In Chapter 8, we will be looking at something brand new to us called an exponential function, and then we'll be getting into its inverse, which is called a logarithm. I did see on the ACT, I think there were maybe 1 or 2 questions on this stuff. So if you're going to be retaking it, this is something that does get covered on there. Not heavily though, so that's why we put it off a little bit later than some of the other stuff that does get covered more heavily there. An exponential function is, first we're going to talk about an exponential growth function. An exponential growth function is a function that begins very slowly. So it has a horizontal asymptote. We've talked a lot about asymptote lately. It has a horizontal asymptote, and it begins very slowly along that asymptote, not showing much going on. And then all of a sudden, it reaches a point where it takes a drastic turn and begins a sharp increase. Okay? Money in the bank. Money in the bank is one of the best examples of exponential growth. This particular graph is 2 to the x. Now, exponential is different than a power equation. So we've done things like x squared, where the denominator or the base is our variable, x, and it's to a power that's always the same, so 2. Okay? In an exponential, the base is always the same, and it's the power that's changing. Okay? So an exponential function is when our variable is up in the exponent spot, and they take these drastic turns. The word exponential gets thrown around a lot in the news. You'll hear stories and they'll say that something's growing exponentially. It may or may not mathematically truly be an exponential thing, but it has become a word that just means really fast. And the reason why people think of this as a really fast thing is because it hits that turning point and takes off. So money in the bank is one of the best examples of exponential growth. That you put your money in, and you let it sit there, it's going to accumulate a little bit of interest over time, and you're not going to see that much of a change. But at some point, it's going to take a turn, and it's going to start growing for you fast. And that's why it's an important thing to learn to invest early when you're not thinking about retirement yet, because then it'll have time to take that turn before you're done. Whereas if you wait and don't start investing your money until you're already older, it's not going to have time to take that turn. But we'll talk more about specific money examples as we go throughout the chapter. Today we're going to be looking at how we're going to graph these exponential functions. So they do have that asymptote, which is a line that the graph will approach but never actually reach. Some properties. It's going to have a y-intercept. The y-intercept is going to be defined by that number in the front. We have a front multiplier. Our x-axis is going to be our asymptote unless we do some shifting on it. Our domain is going to be all reals. I can plug anything in for x because I could do, for example, 2 to the power of anything I want. I can plug any number in there. So our domain will be all reals, but our range is going to be limited by that asymptote because the graph is only going to exist either above or below that asymptote. So we're going to have a limited range on these. To graph them, we're going to look at some charts. So we're going to make XY charts for our graphs here. I'm going to plug in -1, 0, 1, and 2. If I plug in -1, I'm going to have 1/2 times 3 to the -1. Now we got to remember some exponent properties from a while back. What does an exponent of a negative number do? Flips it to the bottom. It's going to make it 1/3. So this is 1/2 times 1/3. A negative exponent flips it to the bottom of a fraction. So this gives us then 1/6. 1/2 times 3 to the 0. Another exponent property. What's anything to the 0 power? 1. So it'd be 1/2 times 1. And when you plug in 0, you will always just get your front multiplier. Because a number to the 0 power is 1, so we're just going to get that front multiplier anytime that we plug in 0. When I plug in 1, 1/2 times 3 to the first, or 1/2 times 3 is 1.5 or 1.5. When I plug in 2, 1/2 times 3 squared would be 9/2 or 4.5. And plot these out. -1, 1/6 is just going to be a small value there to kind of approximate that. 0, 1/2. 1, 1.5, and 2, 4.5. Our asymptote is going to be our x-axis, so it's going to start out flat along there, and then grab those points. Arrows on both ends because it goes on forever. Questions?
You always do -1, 0, 1, 2.
I do. Yep. You can do whatever numbers you want. Those are just always the ones that I pick. It gives us a good picture of the middle. So if I do 3/2 to the -1, what is that -1 going to do to it?
Flip it.
Flip it. So I'm going to get 2/3. A negative exponent flips a fraction, makes it a reciprocal. 3/2 to the 0, 1. Anything to the 0 power is 1. There isn't a front multiplier on this one, so we just get the 1. 3/2 to the first is just 3/2, or 1.5. 3/2 squared. How do I square a fraction?
Put it, or distribute the
Square the top and square the bottoms. Not 9 squared, just 9. Over 4, or 2.25. So our asymptote is going to be that x-axis. -1, 2/3, 0, 1, 1.5, and 2.25. We're not seeing quite as drastic of a turn happening here. It will, we just maybe haven't gone out far enough to see the drastic turn happen. The bigger the base, the sharper the turn will be. So on this one, that base is 1.5. If our base was 1, it would be a completely straight line. It wouldn't take a turn at all. Right? As that base gets bigger and bigger and bigger, it starts taking a sharper turn. And it doesn't have to get very big. The example graph that was given in the notes was just 2 to the x. And that already took a pretty sharp turn. This one's only 1.5 to the x. It doesn't take quite as sharp of a turn. Okay? The bigger that base number gets, the sharper the turn we're going to see. I plug in -1, I'm going to get 2/3 times 2 to the -1, which is going to flip over that 2 and make it 1/2. A negative exponent flips it over, so I end up getting then 1/3. Whenever you plug in 0, you're just going to get that front multiplier because the 2 to the 0 is just going to give 1. Anything to the 0 power just gives 1, so we're going to get the front multiplier in our problem then. Then here I'm going to get 2/3 times 2, or 4/3. 2/3 times 2 squared, or 2/3 times 4, is 8/3. Asymptote of the x-axis, and then plot our points. And this one has a base of 2, so we're seeing a little bit sharper of a turn than we did in the last problem.
How is the 0, 2 or 3?
Anytime we plug a 0 in for x, the part with the exponential is just going to become 1, because anything to the 0 power is 1. So 2 to the 0 is 1, and then 1 times the 2/3 will just give the 2/3. So anytime you plug in 0, you're just going to get that front multiplier. This one has a little something different going on with it. When I plug in -1, it's going to flip over that to a negative exponent, flips it over. So you get -1. Plug in 0 and you will always just get that front multiplier because 2 to the 0 is just 1 times the front number. So you're always just going to get that front number when you plug in the 0. -2 times 2 gives -4. -2 times 2 squared will give -8. Our x-axis is going to be our asymptote. And plot our points. -1, -1. 0, -2. 1, -4. And -8 will be hanging off the bottom of the graph a little bit. So this doesn't look like what we would consider a growth function. It is still called a growth function. It's a negative growth function. The reason why we say it's growth is that it's growing away from its asymptote. So we always read a graph as we read it across a book from left to right. And as this graph moves from left to right, it is growing away from something. Okay? It's growing downward, but it's still growing away from something. So we do still call this a growth graph, but it is a negative growth graph.
I have 2 questions. One, do you have to draw the asymptotes?
You don't have to, but you need to make sure that you know it's there so that you follow it out towards the side.
And then why will you always get the front number if you're assuming that you're multiplying it by 0?
You're not multiplying by 0. Anything to the 0 power is 1.
Oh.
That's our rule of exponents that we learned a while back. Anything to the 0 power is 1. So why do you think this one ended up upside down and was a negative growth graph instead of a positive growth graph?
Because the -2.
Because the front number was negative. Okay? So when we have a negative multiplier in the front, that's going to flip our graph upside down to be a negative growth graph instead of a positive growth graph. We're going to shift our graphs around now. Shifting graphs when they're exponential is exactly like shifting graphs with any other type that we've done. So we've looked at how to move around trig functions. We looked at how to move around rational functions. We looked at how to move around different types of functions. And the beautiful thing about functions is they all follow the same rules. So anything that is attached to the x is going to shift side to side, but backwards. Okay? Anything that's added or subtracted from the whole function is going to move it up or down in the direction that it sets. So the first thing we're going to do is take care of moving around our function. So what is that x minus 1 going to do to our graph?
Shift.
It's going to shift it which way?
Right.
To the right one. And with an x is side to side and it goes backwards of the direction indicated by the number. So minus 1 is really going to move us over to positive 1. What's that minus 4 going to do?
Come down.
Down 4. So we're going to go right 1 and down 4. Then we're going to create a chart for the parts of the equation that we haven't used yet. So we haven't used 3, 2 to the x. When I plug in negative 1, it's going to flip over that 2. When you plug in the 0, you're just going to get the front number. When you plug in a 1, 3 times 2 to the first is 6. And a 2, 3 times 2 squared is 4, times 3 gives 12. Now when we plot these, since we shifted our graph, and what we're really plotting is not the entire equation from before, we need to plot these from our shift lines. So pretending like where those red dotted lines meet is our origin, we're going to plot them from there. Since we didn't plug it into the whole original equation, we just plugged it into the non-shifted part of the equation. So I'm going to, from where those red lines meet, go back 1 and up 1.5. 0, 3. 0.6. And 12 will be a little bit off the top. Where do you think our asymptote's going to be? At the dotted line. So before it was at our axis, it can't really be at our axis now because we crossed it, but it's where we bumped our axis to when we moved the whole graph down 4 spots. This problem also asks us to consider domain and range. Domain for exponential functions is always going to be all reals. We chose to plug in -1, 0, 1, and 2, but you can plug anything into an exponential. Okay? I can do 2 to any power. If I do 2 to a negative power, it's going to get really big, but I can do it. I can plug anything I want in. So our domain will always be all reals. Our range is limited. Range is the y values that you get out of the graph. And there's a part of this graph that this line is never going to touch. And where is that? It's never going to touch anything below that asymptote, right? So it's not going to cross that line, means I'm never going to get anything below that asymptote. I'm only going to get from the asymptote to up. And I'm not actually even going to get that asymptote because it just gets really, really close to it and it never actually touches it. So range is a y value, so we use our y variable. Is it above or below a value? Above, because it's above that line. And what line is it above? -4. So our range is determined by that asymptote. It's not going to be equal to, okay? It's just going to be a greater than or less than because it can't actually touch the asymptote. It just gets really, 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 really close to it. Okay. Questions on shifting, plotting, or domain and range? All right, first thing we need to do on this one is shift it. What's the -2 going to do? To the right 2. And what's the +1 do? Up 1. Then we're going to make our chart. Ignoring the shifts. When I plug in a -1, it's going to flip over that 3. It's going to give me 2 times a third, or 2/3. When you plug in 0, you always get your front multiplier, because 3 to the 0 is just 1, so 2 times 1 is 2. Plug in 1, and I get 2 times 3, which is 6. And 2, and I get 2 times 3 squared, which is 18, and I probably won't be plotting that. Okay? If you can't fit them all in the graph, that's totally fine if they get too extreme. Exponential functions can get very large very quickly, so if they get too large to plot, that's fine. We just need enough points that we can see the curve of the function. So from the shifted asymptotes, or from the shifted axes, we want to plot these points. So from where those red dotted lines meet, back 1 and up 2/3. Over 0 and up 2. Over 1 and up 6.
How is there still a squared in that 3 on the bottom?
I was plugging in a 2, so the x is becoming a 2, so that's the squared. And then 3 squared is 9, times 2 is 18. Now remember, when we shift, the shifted line is our asymptote. It was easier to remember in the last one because we had to cross the axis, and so then we kind of say, oh yeah, it can't be the axis because we had to cross it. But in problems like this, a lot of students still want to bring this all the way down to the original x-axis. Okay? It can't. Okay? It's going to stay at the shifted line is going to create our asymptote. The entire graph, including the asymptote, was bumped up one position in this. Okay, so that shifted line creates the asymptote. Be careful of that in the graphs that move up. When the graphs move down, it's a little bit more obvious that you're not going to like start at the axis and then take a bump to grab your points. But here, a lot of students want to bring it all the way down, so make sure we keep it at the shifted line. Domain and range. Domain is going to be all reals. Range is a y value. Is it bigger or smaller than something? Bigger, and what is it bigger than? 1. Okay. That horizontal asymptote is going to define our range. Questions? Alright, what is the plus 1 going to do?
Move it to the left.
Left 1, and what's the minus 2 do?
Move it down.
Down 2. When I create my chart, I'm just going to be working with -3 to the x. So I'm going to have negative, and it's going to flip over that 3. So I just get -1/3. When I plug in 0, I just get the front number. What's the front number here?
It's -3.
And it's like -1 times 3 to the x is really what this problem is saying. So that negative is really the front number. So we're just going to get -1. And plug in a 1, we'll get -3. Plug in a 2, and I'll get -9. Plot those from the shifted lines. So from where the red lines meet, back 1, down 1/3. Over 0, down 1, over 1, down 3, and that's all I can really fit. Start the graph at the shifted line for the asymptote, not at the original axis. Domain will always be all reals for an exponential because we can plug in anything we want for x. Our answers just get kind of crazy small or crazy big, depending on which way we're going. Range, y, is it greater or less? Less, and what is it less than? -2. Since this is a below graph, we have a less than here. It's below the line of -2. Your homework is from 8.1.